Hi, this is Professor Fernandez, and in this video we're going to work out an example on determining convergence for sequences. This example comes from the notes for lesson 4 in this Calculus 2 course, and if you are interested in downloading those notes or accessing the other resources for the course, head over to the site where you'll find this and other goodies. Okay, so let's take a look at what the example says. Determine whether the sequences below converge or diverge. So I'm going to zoom in here to remind you what it means for a sequence to converge or diverge. So we talked in a video in lesson 3 about a sub n as being the closed form version of a sequence. So if the sequence's starting value is k and it's an infinite sequence, this would be a very compact way to represent the sequence. As a quick example, something like 1 over n starting from 1 to infinity. This generates the sequence 1, 1/2, 1/3, and so on. What does it mean for a sequence to converge? Well, if I take the limit as n goes to infinity of a sub n and I get a number, L, then we say the sequence converges to L. If, however, I take the same limit and I don't get a number, in other words, it doesn't exist, it tends to infinity, just oscillates, never settles down, then the sequence diverges. Okay, so going back to our running example here, a sub n here is 1 over n. And I'd like to then calculate the limit as n goes to infinity of 1 over n. So we are back then in Calculus 1, right? We're calculating limits as n goes to infinity. There is a limit that we have calculated, you've probably done it before also, that looks very similar to this one, which is limit as x goes to infinity of 1 over x. Notice the change in letter, right? Here we're thinking of x as a continuous variable. When I plot this function, 1 over x, at least for positive x, it looks like that. Okay. Whereas over here, we're thinking about n as a positive integer. So usually n starts at 1, right? Certainly for this sequence. So if I were to plot this sequence, it doesn't look like this nice curve. It looks like a bunch of dots, right? However, at n equals 1, 2, 3, 4, 5, right, it matches the same y values on the function 1 over x. So another way to say this is that the function 1 over x interpolates the function 1 over n in a way that makes sense that you would think. You could certainly interpolate these points this other way with some other function, right? That would not be 1 over x. But 1 over x is the most, I would say, natural function that interpolates 1 over n. Why is all of this important? Well, because, there's a subtlety here, right? In calculating this limit, we learned how to do this in Calculus 1. In calculating this limit, n is not a continuous variable, right? So we're doing this here. We're looking at where dots head. So we're still thinking about limits, but we're not exactly doing what we did over here, working with a function of a continuous variable. So is there, question mark, is there a link between the two? And the answer is yes, right? That's what's down here. So I'm just going to review this theorem real quick. Again, this is in lesson 4. What does it say? Suppose I have a sequence, starting value k. If f is a function such that a sub n equals f of n. In other words, the terms in the sequence are the outputs of the function, right? And it so happens that the function tends to L, then the sequence also tends to L. So in other words, this theorem, what it does is that it formalizes exactly what your intuition would expect from this picture, right? 1 over x, as x goes to infinity, tends to 0. We talked about that in Calculus 1. There's all sorts of ways that you can rationalize that. And therefore, because 1 over n is part of the function, is literally like certain y values, namely when the x values are positive integers, right? Because 1 over n is the positive integer x value outputs of 1 over x, if this tends to 0, then of course this limit should also tend to 0. That's all this theorem is saying. So if I were to simplify it, I would say what the theorem tells us is that we can treat limit as n goes to infinity of a sequence, right, for purposes of convergence divergence, as if we were doing limit as x goes to infinity of a sub x, if you will. So we can use all the techniques that we learned in Calculus 1 to help us out. Now, there is one subtlety that I do want to point out, and this is a college level calculus course. So this is the place to point out these subtleties. This theorem, if I zoom back in here, says, has a bunch of hypotheses, right? First of all, we have an infinite sequence. This is a theorem about infinite sequences. Second of all, f has to be a function, fine. And the terms in the sequence have to be outputs of the function, okay. This is really the condition here. If the f of x function tends to L as x goes to infinity, then the sequence tends to L, okay. One important thing that the theorem does not say is if limit as x goes to infinity of f of x does not exist, then limit as n goes to infinity of a sub n does not exist. Okay, that's a separate statement, right? And at this point, I would encourage you to think about a slightly different way to analyze sequences, right? So if you are going back to the definition of convergence and divergence for a sequence, right? What it means for a sequence to converge is that it approaches L. That's where I would use the theorem that I just talked about, because it's a theorem and because it allows you to use everything you learned from Calculus 1 to port over that information about limits as x goes to infinity and all those sorts of things, right, to this new setting. Divergence is a different monster altogether, right? So divergence is fundamentally about the limit not existing. You don't need any fancy theorems for that, as we'll see in a minute with the examples that we'll talk about. Usually it's pretty clear when a sequence diverges, right? And this fundamental intuitive understanding of the limit is really all you need. You don't need anything fancy. Okay, so let's go then to those examples. So let's talk about the first example here. So we're going to determine whether the sequences converge or diverge. Kind of like what we did in the previous video, in the lesson 3 video, we're looking for patterns. We're looking to unpack the sequence for information that is hidden in its representation. So you could take a few different routes here with this one in particular. You could say, I'm gonna simplify this a little bit. This is 1 to the n over 2 to the n, all of that times 3. And then 1 to the n, this is always 1, so it's really 3 times 1 over 2 to the n. So this is really 3 over 2 to the n. That is one way you could go, right? And I think it's pretty clear that as n goes to infinity, 3 over 2 to the n goes to 3 over infinity, which is like 3 divided by a giant number, right? So that tends to 0. And here we can use our theorem, right? If we looked instead at the function 3 over 2 to the x, right, that for the same reason would tend to 0. So therefore, the theorem would tell us that the sequence also tends to 0. So in this way of doing it, right, we say converges to 0, right? That's an answer for the sequence. What's another way to think about it? Well, again, thinking about the patterns that the a sub n representation contains, right? So what's going on here is 1/2 is 0.5. So I could write it in this way, okay? And then now we have taken a different perspective on this. Why? Because this is now literally an exponential function. It's just discrete, right? So it's not the exponential function that looks like this. It's the exponential function where if n equals 1, then this is 3 over 2. If n equals 2, then it's something else. N equals 3, right? In other words, the plot of the sequence are just these blue dots. Nevertheless, right, the sequence is clearly the y values of an exponentially decaying function. How do we know it's decaying? Because the base here is between 0 and 1. So that is another way to see that indeed this sequence is going to converge to 0, because if it's an exponentially decaying function, right, ab to the x, where b is between 1 and 0, tends to 0 as x goes to infinity. That's what exponential decay means. So again, we get the same conclusion in a very different way, right? This isn't really using the theorem. This is really just using, if you will, the pre-calculus of exponential functions and knowing the difference between exponential decay and exponential growth based on the base value. Okay, so I mentioned all that again to expose you to different ways you might tackle these sequences, convergence, divergence problems, to give you some options and opportunities to develop those skills throughout the course. Okay, let's look at part B. Right, this is a very simple sequence, just -1 to the n. And by the way, we're not giving a starting value here, right? So we always assume that n equals 1 is the starting value, unless otherwise noted. Okay, so for -1 to the n, right, what's going on here? Well, I'm going to give you a third way to think about convergence and divergence, right? We talked about using the theorem. We did that here. We talked about kind of unpacking the function, right? That was the second part here. That was the exponential decay. Now let's talk about a third way. How about we graph this? Okay, so -1 to the n, I'm going to graph this sequence. So if n is 1, I get -1. So there's first term. If n is 2, I get -1 squared. So that jumps up to 1. And then n equals 3, -1 cubed. So that's negative. And then n equals 4, you can see where this is going. -1 to the 4th, that's positive. So this sequence is literally just doing this, to the end of time, because it goes off to infinity. So this is a limit that pretty clearly does not exist. There is no single y value that the terms in the sequence approach, right? In fact, every single even indexed term, is 1, so therefore approaches 1. Every single odd indexed term is -1, so approaches -1. There is a theorem, and it falls out of the intuition that we're just discovering here, that if the even terms in a sequence tend to a certain number and the odd terms tend to a different number, then the sequence itself diverges. We don't, again, need to go to that fancy theorem. It's clear here, again, that there is no single y value that the terms tend to, that they settle down on, right, making this limit not exist. Okay, so this one doesn't exist. And then let's look at this last example here. I'm just going to clean things up and record our answer here. How about part C? So we can look at this now through different lenses, right? We now have a few different options. We could use the theorem we talked about. We could try to use some pre-calculus understanding of this particular function. Or number 3, we could plot this, right? Sometimes you want to do all 3 and see which one is going to get you there the fastest. In this particular case, right, the function that's given to us already looks like we have some sense of what's going to happen, right? I'll give you a fourth way, right? You might even want to create a table, right? So that's another option. What if n equals 1? 1 minus a half, okay? What if n equals 2? 1 minus a quarter. N equals 3, 1 minus an eighth. N equals 4, 1 minus a 16th, right? So notice we're always subtracting a smaller and smaller and smaller number from 1. So what's going to happen is that as n tends to infinity, this number we're subtracting is getting smaller and smaller and smaller. So actually, these terms in the sequence are getting closer to 1. And again, this table view makes it easy to see that. Had we plotted the sequence, we'd see the same behavior. N equals 1, this equals 1/2. So there we go. Here's 1 up here. N equals 2 over here, this is 3/4. So, over here somewhere. And then here, this is 7/8, so even a little higher. So you can see the sequence is tending to y equals 1 as n goes to infinity, right? Graphical view. And then lastly, if we try to do this using the theorem, we would replace the a sub n formula by a function which has the same outputs at those n values. And basically, the way you do that is you replace n by x. And then we calculate this limit. If you think back to the recesses of your mind, we have these limit laws from Calculus 1, right? So I can split up this limit that way. And this is 1 minus, and then I can split this limit up that way, right? You don't really have to do all this. This is just the professor and me trying to get you to, remember some stuff that you learned long ago. So this limit is also 1, and the limit down here, this is infinity, basically. So I have 1 minus 1 over a giant number, which tends to 1. So again, that is our answer here for the third one, using any one of these variety of methods, a graphical, a tabular, the theorem that we just talked about. And again, we could also have viewed this as an exponential function, right? 1 over 2 to the n is 1/2 to the n, which is 0.5 to the n. So we could write the function as 1 minus 0.5 to the n. This part exponentially decaying once again to 0. So you're left with 1 minus 0, again, just the 1 that the sequence converges to. Thanks for watching.